Let's look today at the use of the fluid flow calculator provided by engineeringnow.com. The form is a generic form that contains all of the critical parameters required to solve common problems involving fluid flow of liquids or gases. All potential parameters are shown on the form, and the input and output fields are either inactive or active pertaining on the problem at hand. We can calculate the pressure drop of either liquid or gas through an individual section of pipe, or we can calculate the work necessary to move the liquid or gas from point A to point B, that is through either the inlet stream or the outlet stream, and this is equivalent to a solution to the Bernoulli equation. Let's look first at the pressure drop through a single section of complex piping using the example provided. Calculate the pressure drop for water at ambient conditions using the rate of 50 GPM through 100 equivalent feet of 3-inch pipe having a medium roughness. This 100 feet of equivalent length of piping was already calculated by using the system provided, which is one 3-inch gate valve, 3 90-degree long radius elbows, and 58 lineal feet of 3-inch pipe. If we do the calculation, we find that the pressure drop of 0.24 psi is the pressure drop through this length of pipe. The results state that the pipe with an ID of 1.8 inches would be a more optimum pipe diameter. The results for the Reynolds number and the friction factor are also provided. Also, a recommendation for what the typical velocity through this section of this pipe diameter would be. So let's run this calculation again, but we will use 1.8 as the equivalent diameter. But before doing so, we have to find out what the new equivalent feet would be. So if we go over to the fluid flow calculation for pipe equivalent lengths, and we enter 1.8 as our new diameter, we have one gate valve, and we have 10 standard 90-degree long radius elbows. We calculate that the equivalent length of these fittings is 25.2 feet, to which we add the 58 feet of lineal pipe to come to a total equivalent length of 83.2 equivalent feet. So if we go back to our fluid flow calculator, we can use line loss. Again, let's just populate the fields with our example. But we will change this to 1.8, and we will change this to 83.2, and run our calculation again. 2.92 is the pressure drop over this length of pipe, and the velocity is now 6.31 feet per second. Of course, the optimum pipe diameter has remained the same. And you see now our velocity is up in the range of what would be a typical optimum velocity. So let's look quickly at an example for gases. So if we go to compressible, and we do stay with line loss, let's just look at the example provided. In this example, air at 100 degrees Fahrenheit and 20 psi flows through 20 feet of 2-inch inside diameter pipe at a rate of 100 ACFM. What is the isothermal pressure drop of this length of pipe? In this example, we're using isothermal, we could very well have calculated adiabatic flow or polytropic flow. But let's stay with this example of isothermal. 0.23 psi is the isothermal gas pressure drop in psi, and we were provided with the mass flow rate in pounds per second and the mass velocity in feet per second, and the Reynolds number as well. Now let's look at an example of a fluid mover for the incompressible case, that is, such as a pump. In this case, a pump is removing water from an atmospheric storage tank in which the level is maintained at 12 feet above the pump center line. It is drawing water off at a rate of 50 GPM. It has a mechanical seal in which 1 GPM of flush water is entering the pump casing past the seal. The pump is delivering the water into a vessel that is maintained at 50 psig, and the water level in the vessel is 100 feet above the pump center line. The pump suction is 2 inches and the discharge pipe is 1.5 inches. The equivalent length of the suction pipe is 35 feet, and that of the discharge pipe is 250 feet. So we're going to calculate the TDH, that's the total dynamic head, the brake horsepower, the net positive suction head available, and the pressure drop through the suction and discharge lines. So 231.87 is the total dynamic head in feet of liquid. 11.96 is the total pressure drop across both sections of pipe, of which 11.26 psi is that on the discharge pipe. The NPSH required, or the NPSH available, that is 41.99 feet. The brake horsepower is 2.93. And there's some advice about hydraulic efficiency provided. Now, if we look at the same example or similar example of a fluid mover for a compressible fluid, in this case, air is being compressed isothermally and flows through the compressor suction and discharge piping isothermally as well. The volume of air being drawn into the suction of the pipe of the compressor is 5,000 CFM. At atmospheric conditions, the air is compressed to 100 psig. The inlet piping is 6 inches and 20 feet length. The discharge piping is 4 inches with a length of 500 feet, and we're going to calculate the isothermal horsepower requirements. The thermal efficiency of the compressor is 80%. So 0.98 is the isothermal gas pressure drop in the suction line in psi. 5.5 is the mass flow rate in the suction line in pounds per second. Now it is important, and it states it here in the results, that the mass flow rate through both the suction and discharge piping must be identical. And we see here that it is exactly 5.5 in both sections of piping. .5 in both sections of piping. If that were not the case in this calculation, we would have to alter the flow rate in the discharge pipe. This was a guess. We were provided the 100 psig of pressure that had to be compressed to, and we said it was isothermal at 100 degrees Fahrenheit. So this number would be adjusted through a simple trial and error to get those two mass flow rates to be identical to have an accurate result. So this is just a brief example of how to use the flow calculation in chemicalengineering.com. We now have provided that you could use metric units as well as English units, and the calculated results are also in metric or English. So we hope you benefit from this little exercise, a little explanation, and we wish you the best of luck.